So we talked about Dalton's atomic theory. And one of the things in that atomic theory was that all atoms of a given element have the same mass, that they're identical. We now know that that's not actually quite true. We don't have to throw out the whole theory, though. So the masses of the different isotopes are slightly different. Now, when we are doing chemistry, we are almost always dealing with a very, very large number of atoms. And so the difference between this particular atom and that one, the mass doesn't matter. What we're concerned about is the average mass of the atoms. So we can calculate the average mass, we call that the atomic mass, for an element. Whoops, didn't mean to do that. So the average mass, or the atomic mass, is the average mass of an atom. So this is also given on the periodic table. That is the number under the element symbol. These are not integers. So chlorine atoms, the average chlorine atom weighs 35.45 atomic mass units. There's actually no single chlorine atom that has that mass. That's an average, right? If you had two kids who were 10 and one child that was 7, I should have those numbers written out before I start talking about them. Okay, so let's say we had two kids that are 10 and one kid that's 7. So 10 plus 7 is 27. And to find the average age, you divide by 3 and you get 9. So the average age of those 3 children is 9, but none of the children are actually 9, right? Same thing with the masses of these atoms. We're concerned with the average mass, okay? How do you calculate the average mass? Well, it's calculated based on the natural abundance of each isotope and the mass of each isotope. Because unlike, with 3 kids where you can just take their individual ages, add up, and divide by the number, when you're dealing with gazillions of atoms, you can't do it that way. You have to use a weighted average. So this is how it would be done. Naturally occurring chlorine, 75.77%, chlorine 35. That's its mass. The mass of the individual isotope is going to be very close to the mass number. Not exactly the same, but very close. 24.23%, chlorine 37. And so then we can calculate the average mass, or the atomic mass of chlorine. So we take the percentage and we turn it into a fraction, a decimal form, dividing by 100. So 75.77% becomes 0.7577. And you multiply that by the mass of that particle. And you take the other chlorine isotope, its percent abundance was 24.23, you convert that to a decimal, multiply by the atomic mass, and then you take those results, and you add them together. Okay? So the average mass for chlorine is 35.45 atomic mass units, even though none of them are actually that mass. This is on the worksheet we're doing today. So the general formula here, the atomic mass will equal the sum for each of the isotopes. So you take the fraction of that isotope times its mass, and then you add the fraction of another isotope and its mass, and you just do that for however many isotopes there are. So we can do problems like this. Magnesium has 3 naturally occurring isotopes with masses of 23.99 atomic mass units, 24.99 AMU, and 25.98 AMU, and natural abundances of 78.99%, 10%, and 11.01%, respectively. Respectively means those are in the same order as the listed masses. Calculate the atomic mass of magnesium. Numbers like these would need to be given to you. There's no way you get this off the periodic table, what those different abundances are. So we're going to take the percentage and write it as a decimal or a fraction, 0.7899. And we'll multiply by the mass of that isotope, which is the first one, 23.99 AMU. Then we're going to add the decimal percentage. No, that doesn't make any sense. The decimal abundance. So 10% becomes 0.1000 times the mass of that isotope, 24.99. And you should always write this down, because could you do it just looking at the problem? You could, but it's really easy to get confused. 11%, 0.1101. If you've got a percentage that's less than 10, be careful that you don't accidentally change that when you convert it to a decimal. 25.98. And then I can just do this all on my calculator. 0.7899 times 23.99 plus 0.1000 times 24.99 plus 0.1101 times 25.98 equals. My calculator, 24.309099, and the unit there would be atomic mass units, AMU. What about sig figs? So you could be rigorous about the significant figures and look at this product and how that would have 4 sig figs, this product that would have 4, this product would have 4. Then when you add them up, where are the decimal places? I honestly don't care that much about sig figs on these problems. So a ballpark, get it close, is good enough. So what I would do is I would look at the abundance and the masses and see which is the least precise. So here they're the same. They both have 4 sig figs, right? So then I would round off my answer also to be 4 sig figs. So I would keep out to here, and I'd call that 24.31 AMUs. And on mastering chemistry, if you gave it too many or too little, it's not going to mark it wrong. It's just going to say, oh, yeah, that's okay, but hey, not the correct number of sig figs. And you're like, okay, I don't care. Any questions? How do we figure out what those percent abundances are? We use mass spectrometry. We actually have a mass spectrometry, it's hard to say, spectrometry instrument in the next room. We use it on our GC. What this instrument does, well, actually, there's an illustration of it. You take your sample and you inject it into the instrument, and it goes through this area here where there's an electron beam going through that charges the particles. So generally makes a negative charged particle by adding an electron. Adding an electron doesn't really matter that much because the electrons are so teeny tiny. That makes the particle have a charge, and with a charge on it now we can use electrical fields to move that ion. So we have electrical fields here that accelerate the particles. We need these particles to be moving quickly. So we're shooting these now negatively charged particles into this magnetic field. The magnetic field will bend the path of those particles, and how far it gets bent depends on how heavy the particle is. So a big heavy particle is not going to get bent very much by this magnetic field. A light particle is going to be pushed over a lot. And so this magnetic field separates the particles based on their masses. And then we have a detector here that gives a signal when the particles hit. So the information that we get from this will be something like this little graph here. So for chlorine, we're going to get two different signals. One is chlorine 37 and one is chlorine 35. And so we'll take the larger one and say, well, that's 100% intensity. And then we can measure the relative intensity of this and do a little math on those numbers and come up with the percent abundances for the different isotopes. I'm not going to test you on mass spectrometry, but I think it's good to at least have heard, to have an idea, how do we even do that? Any questions?